This is The Chemistry of Plants by Blake and Abby. We're going to go through a virtual lab about the transpiration of plants. Then we're going to go through a PowerPoint that is a little more in depth. In vascular plants, water is absorbed through the roots and carried upward through the stem to the leaves. The force behind this upward movement is called capillary action, a force of attraction between molecules that cause liquids to move up narrow tubes, such as those inside a plant's stem. Some of the water absorbed by the plant's roots is used for photosynthesis, but much is lost to the environment through a process called transpiration. During photosynthesis, tiny pores on the surface of the leaves open to permit the intake of carbon dioxide and the release of oxygen. Because the stomata must remain open for the exchange of gases, large amounts of water are lost to the environment through evaporation. Water that evaporates from the leaves is continuously replaced with water that is absorbed through the roots. Therefore, a plant's rate of transpiration can be measured by observing the amount of water taken up through a plant's roots over a period of time. The transpiration rate can be approximated by measuring the amount of water taken up in a short time through the plant stem. In laboratory, a plant's transpiration rate can be measured by using a potometer. A potometer can be assembled from standard laboratory materials including a ring stand, clamps, a pipette, a burette, a T-tube, glass tubing, and rubber tubing. To measure transpiration rate, a plant spring is mounted on the potometer and the burette and pipette are filled with water. Over time, the plant will transpire and absorb water through its stems. The potometer is constructed in such a way that the plant's water source is the pipette. Therefore, the amount of water transpired over time can be determined by reading the water level in the pipette. The water supply in the pipette can be replenished from the water supply in the burette by releasing the pinch clamp. In this virtual lab, we're going to find out what factors affect the transpiration rate in plants. We're going to be looking at environmental factors such as heat, light, and wind. We're going to go through 4 plants and compare their transpiration rates. So we're going to start with the rubber plant, and we're going to see its regular transpiration rate, which is 4.9. Then we're going to add the heater, and the temperature increased, which caused the transpiration rate to increase to 6.8. Then we're going to add the fan, which acts as wind, and it caused it to increase even more. Then we're going to add the light, and the light caused it to increase as well. Then we're going to get the zebra plant, and its normal transpiration rate is 4.2. And we're going to add the heater, and then we're going to add the fan, which caused it to increase even more than the heater did. And then we're going to add the light, and then our next plant is the devil's ivy, and we're going to see what its normal transpiration rate is, which is 2.9. Then we're going to add the heater, which causes it to increase to 4.1. Then we'll add the fan, which caused it to increase to 4.6. Then we'll add the lamp, which causes it to increase to 3. Then our last one, which is the arrowhead, and we'll see what its normal transpiration rate is 3.6. Then we'll add the heater, and it increases to 6.6. The fan causes it to increase even more to 7.5. And then the light, which causes it to increase to 4. Then we're going to look at a data table and compare. So for the zebra plant, its normal was 4.2 milliliters, and the fan caused it to increase transpiration rate the most. And the geranium had 1.2 normal, but the heater caused it to increase more than the fan did. And the rubber plant had 4.9 milliliters normally, and the fan caused it to increase to 8.4 milliliters. and the coleus had 0.9 milliliters normally, and the fan caused it to increase to 6 milliliters. So overall, the fan caused it to increase the most.
Alright, so let's start our part 2 of our AP chemistry project, and we did the chemistry of plants, of course, by Blake and Abigail. Alright, let's go on to slide 2. Alright, so what do plants need to survive? Most of you are probably thinking, oh, they just need carbon dioxide, water, and some sunlight to survive. But there's a lot more that plants need. Well, not a lot more, but a lot more elements and dependence that they need in order to survive. All right. So like in order to survive, they need specific pHs or interactions with other organisms, such as other plants, animals, or even us humans. Alright, so chemicals needed for plant growth. Alright, so nitrogen, it builds proteins and promotes growth inside of plants. And as you see right here, this plant is yellow. And that is because nitrogen has not built up the proteins to turn it green like it is there. Alright, potassium. As you see here, potassium is all shriveled up and wrinkled up, but it still has a hint of green to it. And that's because the reason it's shriveled up is because it hasn't activated its proteins yet, which it needs in order to turn green fully. Phosphorus is an energy transfer inside the plants. And as you see here, the pinkish greenish one, phosphorus is not completely spread throughout the entire leaf. And so when it does not, plants actually turn pink because they don't have the energy to activate. Alright, so let's talk about transpiration now. So transpiration is the process by which moisture is carried through plants from roots to small pores on the underside of leaves, where it changes to vapor and release in the atmosphere. Transpiration is the start of the water cycle. All right, so this is where plants is where water cycle starts. All right, where it starts at, though, the beginning is in the hydrogen bonding within the water molecules. Oh, my bad. Let me fix that real quick. Alright, there we go. The hydrogen bonding in the water molecules allows the water to flow upward, as in a capillary reaction. So the cohesion within the water molecules allows it to attract to neighboring molecules, as you see, and attach to each other with hydrogen bonding. Adhesion, though, between the xylem and the water molecules, or the cell wall molecules, allows the water molecules to travel upwards through the roots, allowing it to reach the bottom of the leaves and go into the atmosphere. Alright, let's talk about the next slide. Photosynthesis. Basic, easy concept of photosynthesis. Here's a quick picture that we found. All you need for photosynthesis is carbon dioxide, H2O, and sunlight. When you get these three elements, you make C6H12O6, or glucose, and also oxygen, which us humans and other animals need to breathe. So, basic, easy concept of photosynthesis. Alright, medicine. Alright, so many plants are used in medicine nowadays. So the most common is the Taxus baccata, but it's also known as the English yew. It treats epilepsy, which is seizures, and it also treats menstrual disorders. The main chemical in the plant is paxilaxyl, and it allows for the treatment of these disorders. So here's just a quick glance at what that chemical looks like, or compound looks like. As you can see, it has hydrogen bonding throughout the entire compound, which allows it to stay together and help treat that person that is in need. Alright, the next is the opium poppy, also known as, or its original name as Papaver somniferium. Sorry if I butchered that. But opium, as we know, could be used as a drug, but we're not going to write that right now. Opium is actually a very powerful painkiller. And when you inject opium into a site of injury, such as like a gun wound or anything, it actually cuts off messages to the brain from that site of injury, so that you don't know that you are hurt as badly as you think, and you don't feel the pain that you would usually feel without opium. Right? So soil pH. So pH determines how well a plant can survive in a certain region and how successful they can obtain nutrients. Alright, so as you can see, these hydrangeas have different pHs, and with these different pHs, they also have different colors. Alright, so as you see, the more acidic you are, the more bluish you are, color that you have to your hydrangeas. But the more basic you get, you start getting this purple, and then you get this purple pink, and then you're down to this deep pink at a pH of 7, as we know is the neutral equivalence point in pHs. Alright. So, and then here's some more medicine. A daffodil, as we see them, very beautiful flower, but they're used to cure the symptoms or treat the symptoms of Alzheimer's disease, as we know affects of many old people in our society. And Alzheimer's disease, as we know, is a disease where old people start to lose memory of where they are, who they are, and aren't able to comprehend many things in our society.